Hello everyone, this is Himan Hassan, your tutor of organic chemistry. This lecture is present for the University of Kumar for Science and Technology, College of Medicine, Department of Pharmacy, second year. The alkyne molecules or the alkyne group are two carbons with a triple bond between them. If you just look at these two structures that we have, one of them is analgesic drug and the other one antihypertensive drug. These two drugs have triple bond in their structure. Terminal means at the end. The importance of this triple bond make these two drugs work properly. Without this triple bond, these two drugs never work as before. Alkyne, we have to introduce it and we have to discuss a little bit about its structure and nomenclatures. Firstly, between the two carbons, the two neighboring carbons, we have a triple bond. So the hybridization of this molecule is sp, means we have a sigma bond and 2 pi bond and two other molecules or groups adjacent or linked to the carbon-carbon triple bond. It is just like that. I have a triple bond here and I have a group, another group. Between them I have a pi bond on the top and a pi bond on the bottom, plus a sigma bond. So I have here 3 bonds for each carbon. And you know that each carbon atom can make 4 bonds. So we have additionally 1 bond with the neighbors. The hybridization, as we said, it is sp. And it is most electronegative and it's most basic compound. So the alkanes is the less basic one. The alkene is moderate, but the alkyne is the most basic one and most electronegative one. We said that the electronegativity, the density of electron on any carbon leads to having a basic property or Lewis base or nucleophile. So we have 2 types of alkyne. Terminal, that means the triple bond is at one of the ends. I have a triple bond at the end of the carbon chain. So if we have terminal alkyne, we should have a hydrogen atom directly bonded to the triple bond. It is like that. Carbon, 3 bonds, and here I have a hydrogen. This is called terminal, but the other one is non-terminal, is internal. Here I have a group, something. Here I have another group of something. Okay, so that is the difference between terminal and non-terminal alkyne. Their general molecular formula is CnH2n-2. So the number of hydrogen usually is smaller by 2 than the number of carbon. Let's try on that structure. I have 1, 2, 3, 4, 5 carbon. Okay, so the number of hydrogen is double minus 2. 5 carbon, 3, 4, 5, 6, 7, 8. While I have 5 carbon, 5 multiplied by 2 is 10 minus 2 is 8. So I have 8 hydrogen as we just explained it. The bond angle here is 180. So it is linear. It is linear. The triple bond itself has a basic property. The triple bond has a basic property. But the terminal hydrogen has acidic properties. The terminal hydrogen has acidic properties. The IUPAC nomenclature, as the other structures that we have studied, are very clear and easy to remember, easy to assign. We should have a parent chain with a triple bond, ends with YNE, alkyne. We may have internal alkyne with a di substituted and we may have terminal alkyne with mono substituted. We have some common names. The most common one is acetylene. Acetylene oxyflame is the very strong blue flame that the temperature reaches more than 1000 degrees Celsius and it can burn iron. The stability, as we said, like the alkene, the more substituted, the more stable. If we have less substituted alkyne, it is less stable. The more highly substituted internal alkyne are the more stable. So the number of groups that we have here and here makes the stability higher. So thermodynamically is less stable than alkene to greater degree of alkene and are less stable than alkene. What does it mean? If you remember that we said double bond is unstable comparing to the single bond. While alkyne has two double bonds, it's supposed to be much less stable than alkene. And it is true, because we have two pi bonds, 2 degree of unsaturation and degree of instability. The nomenclature of these three structure is acetylene, ethyl acetylene, ethyl methyl acetylene. How we have received the name for that one? If you take this part, it is ethyl, and this is acetylene. That is why we called ethyl acetylene, because this one is acetylene. For that one, this is methyl, and that one is ethyl. The smaller one in between, acetylene. So, ethyl, methyl, acetylene. And we are following alphabetically for the common names. Some other examples. Remember, we have to choose the parent chain and numbered in the heavier side. Numbered in the heavier side. So I will choose that one. As the parent chain. Then I will number it. 1, 2, 3, 4, 5, 6, 7. This is heptane. 7 carbon. We have it. Which side should I select? Here at number 2 I have methyl. And number 5. If I number it here, number 3 will be ethyl. Because the branches are closer here, I will say 1, 2, 3, 4, 5, 6, 7. At carbon number 2, I have a branch. 3, 4, 5, I have another branch. So I would say 2, 5, dimethyl, 3 heptane, because I have a branch here and I have a branch here. If we look at that structure, what I would say, that's the parent chain. Ethinyl cyclohexane. Why? Because the bigger structure is hexane. Let's take this example. At carbon 1, 2, and 3, what I have? Triple bond. So I would say 1, 3 dash hexadiene. Why? Because I have 1 alkyne, 2 alkyne. For this one, I have a triple bond and I have a double bond. Which one is closer? That one. Number 1, 2, 3, 4, So at number 5 and at number 1 and number 4 I have double bond and triple bond. At 5 what I would have dimethyl. So let's draw that structure. That's a triple bond. 1, 2, 3, 4. That's my double bond. And here I have methyl. So at carbon 1 I have triple bond. 2, 3, 4 I have double bond. At 5 I have 2 methyl. But one of them will be the parent chain. The other one is methyl. I have 2 methyl group. One of them will be the parent chain like that. I'm sorry, I cannot change the color of the pen. This is the parent chain. At carbon 5, I have methyl. And for the rest of the molecules, we are following the same scenario. Remember, that is one of the rules of nomenclature. The longest continuous chain has 8 carbon atoms, but 8 carbon chain doesn't contain both functional groups. Therefore, the compound is named as hexyne. In from alkene, YNE, ine from alkyne, because the longest continuous chain containing both of the function groups. If we follow the much longer one, doesn't occupy both of the function groups. So I would say follow that, because that is the longest one containing both of the function groups. Physical properties of alkene, it is nothing to memorize it. Just understand that we have some information in its physical properties, which is important for your 3rd and 4th year when you are doing the medicinal chemistry. Physical properties are important to know. Alkyne are non-polar. They are non-polar, so they are not soluble in water, but they are soluble in non-polar organic solvents. Because we have pi bond, the pi bond has much electrodensity compared to the rest of the molecule, and it has a basic property in its double bonds. Typically, we call it nucleophile. Why nucleophile? If you remember, we said that negative charge, lone pair of electron, double bond, and triple bonds are nucleophile, while the positive charge, cation, partial positive molecules, empty orbitals are all electrophile. So this is nucleophile because it has a triple bond. Typically undergo addition reaction. Why addition? Because we have a double bond, we have deficiency in number of hydrogens, we have degree of unsaturations. In order to be saturated, we can break down the pi bonds. As we said, the pi bonds are reactive. Comparing to the single bond, pi bonds are much more reactive. If we have 2 pi bonds, means we have 2 degrees of unsaturation, means it is even more reactive than alkenes. The hydrogen is acidic. This is basic, the triple bond. And the pK is 26, and this is the comparison between the pK of alkyne, and the basic compound. If you look at the alkyne, the pKa is smaller than ammonia. The pKa is smaller than ammonia. You know, pK is equal to minus logarithm of Ka. Look at the basicity. This is HCl, very acidic, carboxylic acid, acidic, protonated amine, acidic, water, pH 7, starting basicity, but less basic than ammonia and less basic than alkenes, but more reactive than alkanes, more reactive than alkanes. These are the rules of nomenclature. It's a recall of the previous lecture. We don't want to mention it here because we have mentioned in much detail in physical classes and also revision online classes in chemistry of alkanes. The bond dissociation energy is 2 kcal, 200 kilojoules. For the double bond is 152. The difference between triple bond and double bond is 48 kcal for the second pi bond. This is the comparison between them. You see that in their figure here we have 200 kcal sigma bond and 2 pi bond. But for the alkene, 1 sigma bond, 1 pi bond, 152. So the second pi bond, the extra pi bond that we have, it requires only 48. Both of the carbons has triple bond are weaker than the carbon sigma bond. For sure, the pi bond is much weaker than the sigma bond and easily broken. As a result, alkyne undergo many addition reactions, means adding something to the double bond. If you look at the structure here, we have drawn the molecular orbital structure. Each carbon has 4 electrons in its outside. 1 in sigma, 3 in pi. In that case, 1 pi orbital and 1 sigma orbital hybridized and form sp orbital, but still we have 2 unshared pi orbital, which is py and pz. These 2 form the pi bonds. If you look at the structure, we have the sigma bond here. We have the sigma bond, but I have a pi bond, another pi bond, a pi bond here, another pi bond. This pi bond will form these pi orbitals form the pi bond. It will form a cylindrical shape everywhere around the sigma bond, like that. These 2 together, these 2 and these 2 and these 2. It's like a cylinder here and here, everywhere covered with electrons. That is why the triple bond must be straight and the angle must be 180. We cannot have cycloalkyne except cyclooctane. Why? Because we need 8 carbons joined together in order to allow this bond semi-straight to be like 180 degrees Celsius. We need 4 carbon and the other 4 carbon, it's like a crown. This is 1, 2, 3, 4 and the other 1, 2, 3, 4. Because this pi bond doesn't allow this angle and this angle to bend. It should be straight 180 degree. How to make alkyne? How to make greater alkyne? You know that we have acetylene. Acetylene is this small molecule. We can create acetylene by the reaction of Ca C2 plus H2O. It becomes CH triple bond CH plus how many carbon come? 1, How many hydrogens gone? 2 carbons, 2. This is the acetylene plus CaO, gypsum. That is very industrial way of creation of acetylene. Very simply we can create acetylene. Now we have to create a higher acetylene. As we said, these are acidic hydrogen. Both can be substituted with another molecule. Because we said it is acidic, we are using a base, NH2. This basic compound can grab the hydrogen and form NH3 and substitute it with Na. This is a salt and water soluble. Then we bring an Rx. 1 carbon, 2 carbon, 3, 4 carbon. 1 bromobutane. We bring 1 bromobutane. Because this bond is ionic, this bond here is ionic, the negative charge will attack the carbon of the halogen. And the halogen, as we said, it is a good living group and it will expel easily. So this 4 carbon will be linked to the acetylene. What happened to the other side? That side, same scenario will apply. NaNH2 will attack the hydrogen and take it off. The sodium will replace to the structure. And then it will attack the second haloalkane. That one was bromobutane and this one is bromoethane. So that side will be ethane. The ethane will be in the structure and the bromine is a good living group both here and here. Alkyl halide can be obtained from alcohols. How we can get Rx, ROH plus PCl3 or PCl5. Both could be right. To substitute, to change alcohol to alkyl halides, we can use that. Step 1 is acid-base reaction. The amide ion acts as a base, removing the acidic terminal hydrogen and generate acetylide. This is acetylide. Step 2, the nucleophilic substitution reaction. This is nucleophile. The nucleophile will attack that electrophile. Wherever we have a positive charge, it's electrophile. Wherever we have a negative charge, is nucleophile. Because negative charge loves positive, that's why we call nucleophile. Preparation of alkyne from corresponding alkenes or alkanes, or from alkyl halides. So from different sources we can prepare alkyne. Imagine we have alkane minus H2 becomes alkene, minus H2 becomes alkyne. If we have RXX minus HX become alkene, minus another HX become alkyne, like we have it here. The 2 pi bond of alkyne can be formed by 2 consecutive elimination reaction. What is elimination? Means unsaturated molecule become unsaturated by removing an HX group. The good living group is halides, the bad living group is OH. That is why the OH should be substituted to RX, then expel from the structure. We said that we need a strong base to remove these hydrogens. The mechanism of the reaction is as simple like that. It is not included for the exam, but I might bring it back to the assignments that you will have before the final exam. This is the base that we have is NaNH2 will take the hydrogen, the negative charge will return, the bromine will go away. Second one, the same scenario. The second hydrogen will be taken away, a triple bond will form. The bromine is always good leaving group. Remember, chlorine and bromine are good leaving group. The OH is bad leaving group. How we change the OH from bad to good leaving group? By adding a proton. So, elimination of alcohol reactions could be done in acidic medium, but elimination of RX could be done in basic medium. The reactions of alkyne. We have two reactions, it's very, very important. Lindner catalyst and ordinary catalyst. Please don't forget these two. Like the other pi bonds, alkynes pi bond will undergo addition reaction by addition of H2 with using Lindner catalyst. What is Lindner catalyst? These three together. Quinoline, lead salt, and palladium calcium carbonate. This is the powder, absorb the other two, this powder. So this is called Lindner catalyst. This catalyst will form cis product. That is the definition of Lindner catalyst. Okay? Consists of palladium supported by calcium carbonate which has been poisoned or contaminated by lead acetate and quinoline. This is lead acetate. The product is syn addition of hydrogen. That is why it gives cis structure. Reduction of alkyne. Reduction of alkyne. By using NaNH2, these two hydrogen can be eliminated, form a triple bond. By addition reaction of ammonia and sodium or lithium at minus 78 degrees Celsius, it will give us a trans product. So alkyne by sodium or lithium with the presence of ammonia will give us trans product. Alkyne with H2 by Lindner catalyst will give us cis product. The mechanism of Lindner catalyst is just like that we have it here, and you can expand that from internet. And that is the ordinary catalyst. If you remember that catalyst, this one, that's the mechanism of the reaction that we have it. Remember, it's free radical reaction. Free radical reaction we studied in chapter 1. Homolytic cleavage, the electrons of the bond will be distributed equally. Each will take one electron. It is only 3 steps. The sodium transfer an electron to the alkyne, giving a radical anion. Radical anion means what? I have an anion, I have radical. First, the sodium will give 1 electron to the alkyne. So it has 1 electron, this is negative, and the pi bond will break down. So I have radical anion. Radical anion. How? This dot will go here. And from that I have a dot. This double dot together, this is negative charge. And this is a radical. So this is radical anion. Radical anion. Radical and negative charge. And the negative charge will attract this hydrogen. Attack this hydrogen. And saturate the acid. And the other one will form a bond. Then the same scenario happen again. Sodium will give us 1 electron to the side, and the other side will be given by the sodium as well. That is why it is trans, because there is time to rearrangement and form more stable product. Same scenario here. Explain it in that structure. So that one, that structure is the same as this one. So another addition reaction is XY addition. Could be cis or could be trans. It depends. If there is a time to rearrangement to change the bond's orientation, it could give us trans or could give us cis. So by breaking down X, Y, another time X, Y, that's why we have X, X, Y, Y. To simplify it, the triple bond of alkyne by 2HX addition becomes alkane. Dihydrohalogenation by 2X2 tetrahalogenation, or dihalogenation, because halogen is X2 always. And an important reaction, like we studied in alkene as well, and we will study again in alkyne. Hydroboration oxidation is anti-Markov and mercury addition. Mercury sulfate addition with the presence of H2SO4. This gives us aldehyde because anti-Markov. This gives us ketone. It is Markov-Nikov. Hydrohalogenation and electrophilic addition. A triple bond with hydrohalogenation. Hydrohalogenation form that. Another time, double hydrohalogenation. Remember, if the 2X are on the same carbon, called geminal. If the 2X are on neighboring carbon, called vicinal. And to not forget, that molecule helps formation of PVC, polyvinyl chloride. I have a double bond and a chloride, plus a double bond and a chloride, plus a double bond and a chloride. These form a sequence like that. Chloride, chloride, chloride. This is by N called PVC, polyvinyl chloride. The plastics that you have in your window or sewage water tubes. There is HX addition for HBr and HCl. The mechanism of the reaction is just like the alkene, we have it. The pi bond will break down unequally heterolytic cleavage. The pi bond will attack the hydrogen and the bromide will attack the positive charge twice. First, to form a double bond, like we have it. The pi bond attack the hydrogen and the bromide will attack the positive charge. Alkene, then the second case, part 2, is similar exactly. You may ask a question, why in both cases we have the positive charge at that place? Because this carbon is primary and this carbon is secondary. Primary ion is less stable than secondary cation and less stable than tertiary cation. Addition to the double bonds are following that rules in terms of stability and rearrangement. We studied that in chapter 2. Yeah, as we have it here, attacking to the hydrogen, negative charge attack the bromine. This step is slow step, and here the breakdown is again from the double bond to the hydrogen, sigma bond, cation here. This is secondary, that is secondary, and this one is primary. That is why there is no rearrangement. According to that rule, tertiary much stable than secondary, secondary is much stable than vinyl or vinyl, much stable or nearly stable than primary, primary much stable than vinylic, primary. This is vinylic secondary, vinylic primary, and much stable than methyl. The very least stable, this one, and the very most stable, that one. Gain the double bond addition. That's the mechanism in detail. This is not going to happen because this is less stable and that is stable. Halogenation addition, X2 addition to that. Again, the X2 will break down heterolytically. The X2 will break down heterolytically. This becomes positive, that one negative. Always the pi bond will attack. Always the pi bond will attack. And we have this triangle, and usually it's in the opposite side. Why? Because here there is no enough space, while on the other side we have enough space. Hydration, addition of H2O to alkyne in the presence of mercuric sulfate. It will form enol, en from alkene, ol from alcohol. And then this unstable molecule becomes ketone. Enol changed to ketone. How? By rearrangement. By rearrangement. How? I have a lone pair of electron will come to here, and this pi bond comes here. The negative charge will attract the hydrogen here. So the hydrogen is gone, become a double bond, carbonyl. This is called carbonyl, and the rest of the structure remains as the same. This is eno-ketolate exchange called tautomerization. This is called tautomerization, when the enol changes to ketone while the ketone is much more stable. That's the term tautomerization, this exchange between enol and ketone. That is how the process takes place in acidic medium. This is important. Tautomerization in acidic medium. Because we have it. We have that scenario in the drug structure. Hydration to alkyne, addition of H2O, could be E or could be Z. We said that it is forming ketone or aldehyde. Depends on either it's hydroboration oxidation or mercuric addition. This is hydroboration oxidation anti-Markovnikov. Triple bond, the BH2 comes here, then exchange. That is why it is less substituted. That's why it forms aldehydes. Terminal alkyne has a terminal hydrogen. The terminal hydrogen is acidic, which helps a reaction with the base molecules in order to create an acetylide anion. Acetylide anion. You know that IDE means negative ion. The acetylide can react with RX to to form a bigger alkyne. So in order to extend the acetylene to a longer molecule, we need a base to grab the hydrogen from acetylene, and we need an Rx to be added to the structure of acetylide. That is how we created from acetylene we created a longer molecule, even much longer. Sometimes acetylide undergo a reaction which is unfavorable, called E2 production, elimination second order, because of the steric hindrance. While I have a complex alkyl halide, it's very branched. Look at this structure. I have bromine here. I have CH3, CH3, CH3. This carbon is tertiary. Actually, it's quaternary. Tertiary, yes. I have 3 bromines and I have bromine. This molecule undergoes self-elimination because it's unstable. The acetylide will take only a hydrogen from it and change to that product, to methyl propene. That is why in that case, when I have crowded structure of alkyl halide, self-destruction can take place and lead to formation of acetylene. We have SN2 mechanism, means substitution nucleophilic second order. S substitution, N nucleophilic 2 second order. Means 2 means the rate of the reaction depends on 2 things, not just one. If we look at the structure of epoxide, the acetylide will attack it and open the bond. By addition of hydrogen to the O negative structure, it will form that structure. Acetylene, alcohol. We have both in the structure. But which way will go? To the more substituted or less substituted? To the less substituted. Because this is easy. There is 2 very small atoms, which they are hydrogen, while on the other side we have 2 big group, which is methyl. If you compare the atomic number, you will have an idea about the atomic size. Hydrogen is 1 and 1. This is 2. But that one is 15. Both of them are 30 and both of them are 2. This is less crowded. That's why the acetylide will go to the less crowded position. Synthesis. This is important. For everything. How to create bigger acetylene? Because I have methyl here, I need bromomethane. I have ethyl here, I need chloro or bromoethane. What else do I need? Something to take these hydrogen away, NaNH2. So from the target compound, you go to the precursor, to the starting material. let's go back. That is the target molecule. I have to create that molecule. Precursor, precursor, precursor. Then, by the chemical reaction, target molecule will be produced. But what we will do from the starting material to precursor 1, precursor 2, then the product. Thank you so much for your attention. We finished.